Imagine trying to learn a new language with only a handful of flashcards, yet you're expected to keep learning new words every single day without ever forgetting what you already know. That's the exact challenge of continual few-shot learning, and it's one of the most stubborn bottlenecks in modern AI. Most models either collapse when they encounter unfamiliar concepts, or they fall victim to catastrophic forgetting, where learning something new literally overwrites the old. One promising direction is to stop treating an image as a single, monolithic feature vector. Instead, we decompose scenes into reusable object parts. Think of a bicycle not as one memorized photo, but as a collection of wheels, handlebars, and a frame. If a model can isolate these components, it should theoretically handle new combinations and entirely novel concepts with ease. Researchers call these isolated components slots, and the approach is known as object-centric representation learning. But when we actually trained models using this part-by-part strategy, performance dropped. The model fell into what we call the compositional trap. When you train by directly matching individual parts, the gradient updates push each slot to optimize independently. Over time, the slots overspecialize to specific textures, edges, or training shortcuts. They stop learning flexible, reusable concepts and lock into narrow representations. When the model hits a novel concept, those specialized slots fail to align and generalization collapses. So how do we break out of that trap? The solution is a framework we call Compose, built on a deceptively simple principle. Training and inference must follow different mathematical rules. During training, we teach the model holistically. Instead of forcing part-to-part matching, we optimize it to recognize whole classes. This keeps the underlying feature representations clean, general, and resistant to overspecialization. Then, at inference time, when the model sees a new scene, it switches to compositional matching. It decomposes the image into slots and compares them against its learned knowledge, but crucially, it does so without any gradient updates. The weights stay completely frozen. This preserves the generalizable structure and virtually eliminates catastrophic forgetting. Under the hood, this works because of how we handle feature extraction. Older approaches used recurrent state updates to refine slots, which unintentionally mixed spatial logic with visual content and mudded the representations. Compose bypasses that bottleneck. We compute attention-weighted averages directly from the frozen visual backbone, keeping each slot focused on a single, coherent object. To prevent slots from collapsing into identical or redundant representations, we add a lightweight mathematical penalty that encourages diversity without conflicting with the primary training objective. But here's where the real technical challenge lies. How do we enforce that diversity without breaking the model's internal geometry? We need the feature dimensions assigned to different slots to remain independent. If those dimensions start overlapping, the whole system becomes brittle. We tested 3 different mathematical approaches to enforce this decorrelation, and the results revealed something critical about loss function design. First, we tried variance hinge regularization. The idea is to keep the variance of each feature dimension above a minimum threshold. But what we found is that it actively fights the main training objective. While the primary loss is trying to pull similar examples into tight, recognizable clusters, this regularization pushes them outward. You get a constant tug-of-war in the gradient space. The optimizer gets trapped in a compromised state, learning slower and performing poorly on novel combinations. Next, we tested spectral whitening. This is much stricter. It forces every feature dimension to have identical variance and zero correlation across the entire batch. On paper, it sounds like a perfect decorrelation tool. In practice, it's too rigid. It flattens out the natural, uneven structure the model has already learned, essentially erasing the very cues it relies on to distinguish concepts. Surprisingly, using spectral whitening performed almost exactly like turning regularization off entirely. The constraint was so aggressive that it became functionally useless. Finally, we implemented cross-correlation loss. This approach is beautifully minimal. It only penalizes the unwanted statistical relationships between different feature dimensions. It leaves the natural variance and the overall cluster geometry completely free. And here's why it works. The gradient direction of this loss aligns perfectly with the direction the main training objective is already pushing. There's no conflict. The gradients reinforce each other, allowing the model to prune redundancy while preserving its internal structure. The performance difference was massive. By using cross-correlation regularization, we saw a dramatic jump in the model's ability to generalize to completely new object combinations, even when training data was extremely scarce. We also found that a surprisingly small amount of regularization was enough to hit peak performance. Beyond that threshold, adding more mathematical pressure just yielded diminishing returns. Despite the sophisticated theory behind it, the whole system is incredibly lightweight. It adds less than 1% to the model's parameter count and runs in real time. What does this teach us about building better AI? It's not enough to just slap a regularization term on the loss function. We have to understand how the mathematical structure of our objectives interacts with the learning dynamics of the network. Sometimes, the most powerful tool is the simplest one that leaves the right degrees of freedom untouched. By letting the model keep its natural geometry while gently pruning redundancy, we unlock a level of compositional understanding that feels remarkably close to human reasoning. It's a reminder that in machine learning, how you train a model is just as important as what architecture you build. If you want to dive deeper into the math, the code, and the full ablation studies, the paper is linked below. I'll see you in the next one.